This conference will now be recorded.
Hello, I want to welcome all of you on our next webinar. Topic for today is design and control of manufacturing processes in confectionery industry using ADOxx tools, and our presenter today will be Ion Dan Mironescu. So here you can see bio of our presenter. He's associate professor at ULBS, and he works at Faculty of Agricultural Science, Food Engineering, and Environmental Protection. Before we begin, few technical aspects. We are using GoToMeeting, GoToWebinar, so all microphones should be muted. If you have questions, please expand the pane and use either chat or questions functionality. So this is for technical aspects. This session is recorded, and afterwards, of course, it will be available on our website. And now, without further ado, I would like to give floor to our presenter. So, Ian, floor is yours.
Yes, thank you very much for the presentation, and hello to everybody. Thank you for the occasion to present you the work of our group here at ULBS related to the use of the ADOxx for the design and control of manufacturing processes with special application on the confectionery. Why confectionery? You have seen I have a double specialization. I'm also a food engineer and a computer engineer, so I was a very good user and test case for this kind of application, and we use such tools in our both educational and research activity. So it was a good start point and use case for this application. So I will introduce a little bit in my presentation. I will start with the introduction in which I fundament and I present why we should do this thing, why we should develop tools, because the tools are not completely developed, but we need such tools, and we try to make it. We are on the way to do it in the framework of DigiFoF. I will present a little bit the tools, what we use, what parts of ADOxx, and why ADOxx is very good suited for development and for running such tools. Then I will focus on the needs and what we have done on the three levels that comprise this general design or design necessity in manufacturing industry, mainly the design, what we normally call, because design is everything, but design, through design we normally understand the layout or the structure of the system, the operation of the manufacturing system, and the control. I will shortly after that underline how we try to train, so the educational part on the same direction of developing the designer skills for the manufacturing system and for the factory of the future. And after that, I will summarize the presentation, and I expect your question and I try to answer them. So why are such tools needed? Confectionery industry is a particular branch of food industry in that is more suitable or more similar to manufacturing industry with a very large product palette. So using some machine, some workstation that you can combine, not randomly, but you can combine with a very many possibilities, you can obtain a large amount of product, of type of products. And this is in accord with the demand. So the confectionery market is very demanding. Every time it needs more product, more variety, more packaging systems, more because confectionery is a present. It must be attractive, and it's also in many cases a marketing vehicle. So this is the demand. And food engineer is put in the situation of having the task to design and operate such an ensemble formed from different machines that must work together and produce in time and with according quality the desired product. So the product that comes normally on a command. So how we can do this and what should we use as a tool to cover all the aspects of such a design. So in this regard, ADOxx is a very good tool because it allows all aspects to be covered. Because ADOxx allows the meta modeling. That means we can develop domain-specific languages. That is a very good advantages when you want to develop tools with not so steep learning curve, and that allows the specialist in the domain to express the solution and the problem first, then the solution, and then to find the best solution from all. It also has modeling tools that are produced on the basis of this meta modeling or the modeling language, and also offer support for simulation. So you can cover all the aspects that we will see that are needed for such an approach. So for all tools needed in the designing and controlling or developing the control system for a manufacturing system, not particularly the confectionery system, but the confectionery system, like I show you, is a demanding one. So also the requirements are demanding. So what should actually or how can ADOxx help the development of modeling tools that are adequate for use by perhaps not so IT proficient specialists, but food specialists with a good background in their profession, but not so much IT background. So in the first phase, the meta modeling, that I find it very important to also bring in or imply food specialist. You can define the elements of the meta modeling language, the graphical. So for choosing in this stage of the element, the element that are very important for design, and the attributes of this element that are very important for expressing the properties of the system in structural form and also in functional form. Then defining the graphical representation of elements in such a way that the food specialists that use the languages have easy task to choose and to understand the representation or the model representation, and defining the behavior of each element so that it corresponds to the real part, and you obtain some sort of digital double or digital twin of the factory in respect to the functioning, or so that you can evaluate the solution that is a design solution, a design of or the layout of such a manufacturing system. That means a portion, a section of the factory that produce parts or complete confectionery product. So in this direction, we work together. It's not only my work. We work here in Sibiu with my, especially my colleagues, Daniel Crăciunan and Professor Vasile Crăciunan, and we developed a language which is not completely defined, but we try to tackle the small details that can represent such a system. And I will show you some examples to understand what elements are normally needed, how they are in reality, and how we represented them. And in this idea, any suggestion or question are welcome to clarify some aspects from perhaps other point of view. So one element that is omnipresent and is very important, you will see in the later slides, is the buffer. This is a storage facility in which temporarily, normally the raw materials are stored in big storages that can or cannot be automatized, but you need every time a buffer, short time storage to feed the installation. So for the graphical representation, we choose a circle because in the especially in the food industry, most such buffer are circular or cylindrical tanks or recipients, and from above the circle is some for the food engineer recognizable shape. Each of the machine that we represent here from this category have input and output ports, and we have many category of ports identified by the shape of the ports. So the ports are the little circle or rectangle, and the shape discriminates between material ports and information ports. So this is a buffer. It has also some attributes, the storage, the maximal storage capacity and the current storage capacity or number of units, and some that we will find. This is not particularly not circular, but it can be also circular if the cardboard is in a roll, a cardboard storage. Another component of such a process are the workstations. So in principle, many production line in the confectionery industry are mostly only made from such things, so buffer and workstation. With the workstation, we abstracted the category of machines that transform the material. So you can have one or more inputs of material, but when it go out, the material is transformed. And what characterizes such a machine? In this case, you have two ports and one two input ports and one output port. And this is a packaging machine. Is a workstation that is packaging bags with truths. We will see in the example. So it inputs the truths and the cardboard packaging, and after that you have the smaller or bigger boxes, cardboard boxes with truffles, chocolate truffles, because it's confectionery, not anything else. Good. Another element that is many times present in the food and in the confectionery especially are the transport elements. We abstracted here. The line is not very crisp, but we decided that transport lines are, or transport machines are the machines that are not changing the material. So the same material that's enter is also go out. Normally, and at what we look in this case is that the mass and the packaging and the geometrical, so to say, details are preserved. So if I have a number of units on one side, I should have the same number of units and from similar, so not important changes on the other side. But in the food industry especially, we have also some hybrid things like this that is, for example, used to freeze the product. The product is the same, no change in mass normally takes place, and the pieces remain the same, but some transformation take place. That we consider that this is a transport utilage. And also from transport machine, and also from the category of machine, we have the manipulator. The manipulator are normally what we see generally as a robotic arm. But if in this case, the robotic arm has a transport function, and we design it as a manipulator and the transport machine, so in the bigger class of transport machine, because it only moves things from one input port to other output port. Difference to the transport lines up there is that the manipulator can have a bigger flexibility, combining many ports and doing sequentially many transfer possibilities between input and output port. So theoretically, a manipulator can take a material from each input port and put it in each output port. And this gives a flexibility in the layout and in the operation of the manufacturing line. So, from the point of modeling, we have defined a domain-specific language that allows us to model some situation and allows doing that with a more specificity and perhaps a more recognizable aspect than all the other modeling languages or other modeling tools. And I present here, for example, and also for a little familiarization with the other modeling tool that I will use, because we use them in and we intend to use them in cooperation, namely the PetriNet. So you have an abstract representation in the left up corner of the classical philosopher problem. So the four philosophers that are eating and are sitting around the round table, but have only 4 sticks. So it's in some oriental settings. Each needs 2 sticks, and this is a standard problem with distribute and concurrent system or concurrent system, and also for analyzing concurrent system problems like deadlock. Because if each one takes 1 stick, he cannot eat with only 1 stick, but also the other ones cannot eat with their sticks. So how is this relevant for the food industry? Yes, it's relevant because you can have an arrangement like the one in the right corner or the right side, in which you have 4 workstations that are the similar in the flexible manufacturing line of the philosopher, and each of these is fed, so to say, by two manipulator arms or robots or manipulator that feeds to each workstation one type of feeding material or raw material. So each workstation needs both of the manipulators to be fed and to function. And if the control system, because at least this goes to the control system, if the control system is not good designed, and it's not taking account of all problems that can arise in the philosopher dining problem, then you can have the same deadlock in a flexible manufacturing line like in the philosopher problem, with the difference that robots are only feeding, not thinking, like the philosopher. In the right corner, you have the same representation of the same problem with the Petri net, So with place transition symbols. And what I wanted to underline or present here is that, and we have this experience with our students, the left side representation for people that are doing similar layouts, because we use such symbolic layouts to represent the design of the factory, is more understandable and comprehensible than the Petri net, which is one level of abstraction upper. But it can be used, and it is also useful if one explain and present also how you can transform the left representation in the right representation, which should be also easy to do, and we are on the point. I have done this in a more empirical way, but we will adapt, we will try to adapt this also for the new modeling language, to transform from this modeling language to the Petri net. For example, we can associate each buffer, which is very at the hand, with the places, and for example, for the manipulator, each operation that it can do, for example, transferring from the input port to one side or from the input port to other side, with one transition that takes the resource, the token, from the corresponding buffer and put it in the other buffer, and also explain that some part of the Petri net represent the behavior of the workstation. For example, the workstation have two possibilities, like the philosopher, they can eat or they can think. So if you have two positions that represent the state of the workstation, then you can represent the token to see in which point, at this point, the machine is. So this is the part of the modeling, and this helps us to have a layout that can be then transposed easily in a Petri net, because it's a graph transformation, and can be used for the next step, that is simulation. Okay, sorry. For the simulation in ADOxx, and in our case, we use multiple approaches, each with the advantage and disadvantage, and also we intend to explore these approaches. Not all are ready to use, so to say. So the direct way is implementing the algorithm in the ADOxx and have direct support from the modeling language. So the model that is layout, or the layout that the design that is made in the tool or built on the domain-specific languages can be simulated also directly in ADOxx. Another way that we also tried is to transform between modeling languages that are implemented at this point in ADOxx. Web.13 is one of them, so this helps us in big way with only one limitation related to the time simulation, and the method that I have used with our students, and we use currently at this point, is exporting the model to external simulators, which is also um, easy to do. So I put some simulators, and I can present a use case. This is a real line, so to say, a real production line. This production line is producing and packaging. So we have the final product, chocolate truffles, and these chocolate truffles are 2-time packaged. They are packaged once in aluminium foil bag, and many such aluminium foil bags, because I told you in many cases is a marketing vehicle also, are put in cardboard boards in a decorative or ornamental way. So what the whole manufacturing line is composed of 3 distinct sublines or units. So we have a line in the superior part that are making the chocolate truffles and package them in the aluminium foil. You have the second line in the bottom part that makes the cardboard boxes, form them in the form suitable for packaging, and you have the assembly line, the middle line, that is assembling the foils, the bags with the truffles in them, and the cardboard. So the raw material, in this case the chocolate and the cardboard, are brought to the line by use of autonomous guided vehicles, which feed the buffers. The buffers then feed the workstation 1, which is forming the chocolate and giving the necessary composition, and also portioning the chocolate. This is feed then in another buffer, which then put it in the transport line, which is also freezing, so that the chocolate truffle maintain the shape. So this is a transport facility which feeds the final workstation of the line, that is packaging with aluminum foil from the buffer 12, the truffles in the aluminum bags. And this is then put in the buffer to which this manipulator can reach. On the other side, also the cardboard templates are brought to the workstation 3, which form them in cardboard boxes, and the boxes are stored in the buffer 8. The manipulator takes alternatively a number of packages of bags with truffles and a cardboard box, and this is the flexibility of a manipulator. If you have a fixed transport line, you can solve this problem of bringing the two lines, but you have not the flexibility of taking different number of boxes or different number of bags with truffles, and the manipulator can feed both of them alternatively in the workstation 4, where a soft gripping manipulator mix the two components. So from this point of view, this is a workstation, and put it in the buffer, the final product. So this gives, and this is also important, this gives also an information of the layout. So if I see from above, I have the outline of a blueprint of how the section or the floor will will look like. Okay, this is the modeling part. So we are, and this is something that is done. Also, the instrument is in a mature phase, and we can use it. So we can have normally a design of the floor. What can we do with this? Through simulation, we can do two things. We can do a timeless analysis, so only in principle of exploration of the state space of the solution, of our design solution. And this can give us information about the connectivity, about the possibilities or impossibilities. So it can say if some states are reachable, are not reachable, if they are, if forbidden states are reached, and things like that. But more important, and you will see from the operation, is for us to do a time-based analysis, usually based on discrete event simulation, because this gives us on one side information of what really happens, because they are we change from logic, from a formal logic that is classic formal logic to temporal formal logic with possibilities, and if something happens or not happens. And also it gives qualitative information, so we can see if with this layout we can have the desired total production time, we can have, or we can see what and how the resources are used in time, so how much, and we can also appreciate the throughput, how many pieces, how many boxes of chocolates are produced in this total production time. So total production time gives honestly the information how much is from feeding the installation to outputting the installation. And now we come to other operations. So we have made a design, we have analyzed this design from the point of view of which capabilities this design have, and now we must operate it. And the problem is that normally in confectionery industry, the work is organized, and we will discuss shortly, without bothering you with many details, as a flow shop. I will come. So you have many jobs that must be done. It's not economically, and it's not also feasible to do only one job one time. You run many jobs in the same, not in the same time, but concurrently on your line. And from this point of view, the operation in this confectionery and also in all manufacturing industry that has similar condition is reduced to one important problem from also from operational research and from mathematics, that is scheduling. So normally, to solve an operation problem, given some jobs that must be done on our line, is to solve an optimization problem with some specific notation. I'd put it there. The notation is only thing that I want to relieve is the notation is some way abstract, and every time when we talk with our students, and also I think for the learning capacity, is very abstract to formulate such a scheduling problem with the three components. But normally the first component express two things. One, how many machines are, so one, many, or other. And the second thing is how the work is organized. And if you see, and you will see for the other slide, on the other slide, if you see the machines, then you grasp it, what the problem is. Perhaps if you see only one, it's not, but if you see one machine, then you know. And also with the other details of, for example, the number of orders, this should come with the schedule, but the number of machine, the index of machine, and the index of the order, and what a schedule is, it depends on the case. The schedule is a permutation in most cases of the number of the task on which machine I run firstly each task, and also the processing time. If you simulate, then you know that the processing time is the moment from which the part is starting in the first position, and the part to the moment the part arrives at the end position. And also some other concepts or some design concept are better explained. For example, the P is the notation for parallel machines. So you have in parallel, like you have here, three machines that execute in principle the same operation. You can have a flow shop. We will see a flow shop. That means the machines are one after other, and each job should be executed on each of this machine exactly in the order. So if you start with one job, this job will go to the end in the same order. All jobs will go in the same order. And you can have also another types of organisms, for example, the job shop and the open shop. The job shop allows the transfer to different machines, so no order, and the open shop allows every order. And this example here, to which we will come also later, is an example that is only suitable for the three others, for the two last one, because you cannot organize in line. You must have a flexible possibility to redistribute to another machine the parts to be processed, and this goes only if you introduce a manipulator, so a flexible element that can redistribute to other machines the parts. So what are the needs? And perhaps here, because we are also thinking, so the many problems are with only one machine. And in this case, the problem can be solved easy in ADOxx. Why? Because, for example, for one problem, when you try, and there are single objective optimization problems, so you only see one aspect that is important for the schedule. For example, the C, the completion time, or D, the delay, or like is presented here, I try to, on this single machine, to reduce, so minimize the maximum delay. The maximum delay is completion time minus due time for the part. And this is only a sorting. So this is the kind of problem that can be resolved directly in ADOxx, implementing the algorithm that is a sorting algorithm. Other problem, for example, reducing the number of jobs that are late. That means reducing the number of jobs with completion time bigger than due time. This is a little bit more complicated, but this is also an heuristic algorithm, a list algorithm that can be implemented. In the end, everything can be implemented at ADOxx. The problem is only with which cost. Other type of problem, I think, and the discussion can, or further discussion can show this, are more complicated to treat. So, for example, if you want to make a multi-objective optimization of the schedule, in this example is a problem of permutation flow show problems with limited buffers. Limited buffers introduce some supplementary constraint in that a machine cannot cannot discharge in a full buffer. So if a buffer is full, the machine must wait until this buffer is depleted. And this in the simulation is also it's a little bit abstract to explain, but if you see that the buffer is full, the next machine must wait, and so the anterior machine can start to process the next job only when the following machine has ended his current job. So there are dependencies. And such complicated problem generate even for 2 machines or 3 machines like this very complex problem that can be only solved using for example, genetic algorithms or higher genetic algorithms that can also be that are disponible in libraries and can be linked, for example. But one particularity, and was only the idea to present this, is that you can encode the solution and transfer it to an solving algorithm. But good results is obtained if some of the new generation individuals in the genetic algorithm are obtained also using scheduling heuristics. So in this case, a good solution will include both parts that are implemented in ADOxx and parts that are used externally. So this will be a good idea to implement. And we come to the last part, so the control, because to operate in this condition, so I have made the design. I have also a schedule that is optimal, obtained like it was before, but ideally so that the system responds in the good time and with safety and things like that is only when having a flexible manufacturing system that supposed beside a set of workstation that should offer what is named machine flexibility and the material handling system that should allow a routing flexibility, so I can feed each part in every one of the disponible workstation, also complex command and control systems that orchestrate this operation. And for here we have also from our experience the solution, and by combining the two, this is a good use of this, is the synthesis of such systems. So controller synthesis on basis of the Petri net. This is a theorem. The importance is that this theorem is on basis of incidence matrix. So these are the matrix that describes the connectivity of the corresponding Petri net of the plant, and supplementary, we cannot observe everything and we cannot control everything. So this theorem allows you to synthesis automatically, and this is a really problem when the system is complicated. We will see some example in the following slides, but they are simplistic for understanding. But when the system is complicated, the tool help you very much to automatically synthesizing the controller, so to say, the PetriNet controller for the plant for the given task. And what can be the task? The task can be either some constraint. So we have here an example also of a line that is normally current in the industry because it supposes casting something in two molds, the left side mold and the right side mold that are mixed together. You cast, you pour in the workstation one, you pour the material that can be chocolate, can be sugar, syrup can be something that is hardening. You bring together, so to say, the two shells and the product. You hardening the product either by heating or by cooling. That depends on the material. And then you demold, so you cast out the pieces, and you must return the pieces. And this gives on the principle that I give you before, so transition are workstation, buffer are places. You have such a net, and what you want to do is to control the number of pieces in the tunnel, because the tunnel has a reduced capacity. And by using the incidence matrix and the theorem, you can synthesize the controller that limits the access to the tunnel only to the specified number of pieces. Other problem that is very important, and we have discussed about this, is the deadlock control. So the deadlock control in this situation, we have a similar problem with casting, but you have the two shells are similar and are fed by RGV that is a single RGV that feeds both buffers, and this gives, when represented, such a system that is a free choice system, because if you let the RGV to choose which station goes, it can go to only one side and then feed only one side, and it cannot return because it has nothing to take from the other side, and this can go to the deadlock. And also you can synthesize the corresponding controller that assure that the RGV is feeding alternatively one and the other side. And also you can solve higher problems or higher complexity problems, like is here you have this manipulator that should feed each so to say line composed from a buffer and the workstation. The workstation is continually depleting the buffers, so the manipulator should feed them in order that the buffer don't remain empty. And it's one only manipulator that can feed the three places, and the places had a signaling system that says I'm overfilled or I underfilled, and the process must use the manipulator so that no one of the station is empty or they're underfilled. So this is a complex, you see it, and it can be solved, and also control can be synthesized from this, so to have a more complex control than other. So these are the problems that we can solve at this point in cooperation between ADOxx and other tools, or between other tools from inside the ADOxx. and we intend to extend the part or the integration part. This is the integration of ADOxx in this system, and we also train using this system our students. And I wanted in the final to only describe a little bit how we do this. This system and the possibility to model, to have models of the problem, gives us the opportunity to use problem-based learning in so we can easily formulate, having the language, we can easily formulate the problems. The students have lesser problem in understanding the problem. So in the case that they don't see the real system or cannot see the real system, we employ this in teamwork so that cooperation is used, and the teamwork is facilitated by the use of a common language. We have implied the students, even if they have not programmed, but in defining some parts of the domain-specific language, and we solve every problems on every of the three levels. So we solve design with them, design problems, optimization problems, and control problems. In final, we use a competition. So we give a problem with an open solution, and they compete in finding the best solution. Mostly it's a heuristic problem, so we don't have an exact problem. So their quality, their problem solving quality are good put on the test, and they can appreciate how they have formed their skill. So thank you very much for the attention. I want only to summarize a bit what we discussed because it was a little bit long. So we have discussed about the problem. At the beginning, I have presented you the problem, the many possibilities in the product and in the configuration of the production line, the tools that we use and that we try to integrate with ADOxx, all the aspects of the design, then and how the possibility of ADOxx, the possibilities on the three level of ADOxx are used. We then, I presented you the design, the part that we made mainly in ADOxx, or the instrument based on a modeling description language, on a domain-specific language for modeling, and how it can be used for solving the problem and for formulating the solution and assessing the solution and choosing the best solution. We then talked a little bit of the operation and of the scheduling problem that can be at least easier formulated using our tool. And we expect also there is also direction, but time it's not so good to go, and defining also a specific language for scheduling. There are research in this direction, and this is a good point of starting. And also how the control can be transformed from a problem to the tool that solves this, normally mainly the PetitNet, and how it can be solved constraint problem, deadlock problem, and supervisory problem. I also presented in the end our approach to forming the skills in the domain. I thank you very much for your attention, and I'm open for your question. Thank you very much.
Thank you very much for your presentation. I'm waiting to see if there are more questions, but I have one question. At the very beginning, you mentioned several simulation mechanisms, including Snoopy. Could you tell a little bit more what is it?
Yes, Snoopy is a PetitNet tool. It's developed in Germany at Cottbus. The name is a little bit funny, but the guys there that have a very good background in mathematics and informatics have a predilection for the Snoopy. So they have many tools. Snoopy is the tool for PetriNet and is a very capable tool. Every type of is the most capable tool, and from this point of view, you can use any type of PetriNets, colored, uncolored, timed, untimed, stochastic, and even fuzzy. So from this point of view, is a very potent tool, and they have named Snoopy is the PetriNet tools, and they have also some tools that are named Charlie and Marcy, used for the analysis of PetriNets. So formal analysis. This is another advantage of PetriNets.
Thank you
Okay,
very
I
much.
hope
I don't see any more questions, so one more time, thank you for a great presentation. Thank you all
Thank you very
for
much
participating,
also for the
and
attention.
see you soon on the next webinar session. Bye-bye.
Thank you very much. Bye to everyone. Thank you for your attention.
Bye.